Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello, well, look at that volcano. Beautiful this morning. Hi there, now I'm blocking it. So much for beauty. Lesson 21, special relationships within right triangles dividing into two similar subtriangles. Classwork opening exercise. Exercise means do it yourself. Then check to see if you did it correctly. So here we go. So I look at this and I'm like, okay, that's a right triangle. And I know that the two acute angles in a right triangle are complementary. So I'd say the measure of angle A plus the measure of angle C has to equal 90 degrees because 90 plus 90 is 180 and that is a triangle. A is 56.3 degrees plus the measure of angle C equals 90 degrees. So to find the measure of angle C, I subtract 56.3 from both sides. And when I do that, I get the measure of angle C equals 7. So this is now 89, 3, 3. 33.7 degrees. So the measure of angle C is 33.7 degrees, and so is this angle. So X has to be 56.3. So we have angle-angle similarity. Okay, so I had to prove that I had two angles similar. So if this is 56.3 as well. So angle-angle similarity, yes. My explanation's right there, and it's by angle-angle similarity. B says to determine the unknown lengths of the triangle. Okay, well, it's a right triangle, so A squared plus B squared equals C squared. Thinking faster than I could write. A is the side opposite angle A, so that's 3 squared plus B is this hypotenuse. Whoops, time out. The way they named this, okay, they named the right angle B. Sides opposite are the lowercase of the same letter. So in this case, the hypotenuse is B. Be careful. So this would be A squared plus C squared equals B squared. Okay, please be careful with that. Don't always assume C is the hypotenuse and throw it over on the right or you'll get it wrong every time. So this is 3 squared plus C is opposite angle C, which is 2. B is opposite angle B, which is our right angle. So when I do this, I get 9 plus 4 equals B squared, 13 equals B squared. Therefore, B has to equal the square root of 13. And we just take the principal root, meaning positive only. A length can't be negative. All righty. So that is B. So then I look, they're similar, so there has to be a proportional multiple scalar factor. And to get from 2 down to 1.5, my scale factor is 2 to 1.5, but I don't like using decimals, so if I double this, I'll get 3. 2 times 2 is 4, 1.5 times 2 is 3, so my scale factor is 4 to 3. Okay. Okay, so since I know two sides of this triangle, actually I know all three now because B is the square root of 13, I can set up my proportion as 2 over 3 equals 1.5 over, and since this is called X, this is the side opposite little x, so I'll just call it X. So then when I cross multiply, I get 2x equals 1.5 times 3, which is 5 times 3 is 15, carry the 1. 3 plus 1 is 4.5, divide it by 2, and I get x equals 2.25. Okay, so this is 2.25. Now I've already done the Pythagorean theorem to determine these were similar by two angles being congruent. So I've already got the length of B right here. So if I take B, let's see, how could we do this? Well, let me just do the Pythagorean theorem again. So we have this side here, and we have this side here. This would be our A, and this will be our B, and this will be our C, if you will. Okay, well, let's not call it that. Let's just say that this is Z, and this is X, and this is Y. So X squared plus Y squared equals, oops, gotta be careful here. Pythagorean theorem, make sure the hypotenuse is always by itself on the other side. X squared plus Z squared equals my hypotenuse Y squared. Plug in our givens. 2.25 squared plus 1.5 squared equals Y squared. Okay. For some reason, I can't remember what 2.25 squared is. 1.5 squared is 2.25. But what is 2.25 squared? 2.25. 5.0625 plus 2.25 equals Y squared. Yes, 1.5 squared, same as 15 squared, move the decimal. And then when I add these, plus 5.0625, I get 7.3125. So to find Y, I take the square root of that. So I go square root, second answer for that last answer, and hit enter. And I get approximately 2.704. Let's make it an approximation because it's rounded. It's irrational. 2.704. Or you could have just left it the square root of 7.3125. Okay. Page 2 brings us to part C, and it says, explain how you found the lengths in part A. Well, I kind of explained it already, but here we go. Since the triangles are similar, I use the values of the ratios of the corresponding side lengths to determine the length of YZ. So I found the length of YZ by setting up this proportion. Okay. To determine the length of AC and XZ, I used the Pythagorean theorem. Okay, example 1. Recall that an altitude of a triangle is a perpendicular line segment from a vertex to the line determined by the opposite side. In triangle ABC, to the right, BD is the altitude from vertex B to side AC. How many triangles do you see in the figure? Okay, well, I feel like I'm on one of those Facebook things to see how smart you are. How many triangles are in this figure? There's one. There's two. And there's three. So I have the red one here, the blue one here. Move this over just a smidge. Clone, I just want to move it. Okay, and as you can see, the big green one. So there are three. How many triangles do you see in this figure? The answer is 3. And then they tell us the answer before. Identify the 3 triangles by name. Well, the red one, it was with my pen. Can I have my pen, please? Thank you. The red one is triangle ABD. Okay. And I named them with the right angle being last, if you can notice that. D is my right angle, and I set it last. So I'm going to do the same for all of them because we might want to set these up as proportional similarities. So I want to say in the blue one, it's B, C, D, D, C, B, blah, blah, B, D, C, D, B, C. There's 2, 4, 6 different ways to name this triangle, but I would like to name it. Let's see. I said A, B, D. So this time I'll say B, C, D. Triangle B, C, D. And then finally the big green one is A, C, B. There's the 3 triangles. We want to consider the altitude of the right triangle from the right angle to the hypotenuse. So they're talking about D to B. The altitude of a right triangle splits the triangle into 2 right triangles, each of which shares a common altitude angle with the original triangle. In triangle ABC, the altitude BD divides the right triangle into 2 subtriangles, triangle BDC and triangle ADB. So the way they named it, BDC, they named it 1, 3, middle, 1, 3, middle. So you see how these line up like that? I'm going to keep pushing that because we don't even need to look at diagrams. If it is named properly, angle B corresponds to angle A, angle D corresponds to D, and angle C corresponds to B in those 2 triangles. Is triangle ABC similar to triangle BDC? And is triangle ABC similar to triangle ADB? Explain. Okay. Okay, so here's our answer to this, and I'm going to go over it with you on each piece. Triangle ABC and triangle BDC are similar by the angle criterion. Each has a right angle. So triangle ABC is the big green one. There's the right angle. BDC is the blue one. So we're comparing green to blue. They both have a right angle and they share angle C. So angle C is in the blue one. Angle C is in the green one. So by reflexive property, C is congruent to C, and a 90-degree angle is congruent to a 90-degree angle. So that's the angle criterion. So now let's get rid of those purple marks. And then we can say triangle ABC, the green one, and triangle ADB, the red one. You can't see that other red side, so let me move this over just a smidge. Okay, so we're looking at red versus green. And they each have a right angle. This is a right angle in triangle ABD. And the green one is this angle here. So they both have right angles, and each angle shares angle A. So the angle A is in this red triangle, and angle A is in the big green one. So angle similarity criterion. Okay. Okay, page 3 brings us to part D, and they're asking, is triangle ABC similar to triangle DBC? ABC, DBC. ABC is the green, DBC is the blue. ABC, BDC, ABC, DBC. I'm confuzzled here. Are we onto the new triangle? Okay, so they're trying to trick us here. So let's go back, and I'm going to explain what they're doing here. Remember what I said about naming triangles with corresponding pieces. A corresponds to B. Why? Angle A is here. Angle B is here. So if I took this red triangle out it would be the side that shares the hypotenuse. So the angle A corresponds to B in the big green triangle, and B corresponds to D because angle B in the big triangle is a right angle and angle D is the right angle here. And then finally, angle C corresponds to itself, obviously. So we have already said that ABC is similar to BDC, but then I go here and they changed it from BDC to DBC, and now they're saying A is corresponding with B. So if I go back, well, let's just go to the last. They still have C corresponding with C, B corresponding with B, and A corresponding with D. A does not correspond to B. Why? Here's A, and B is a right angle. A is definitely not 90 degrees, so they rearranged the names to try to trick us, and so therefore the answer is triangle ABC and triangle DBC are not similar because their corresponding angles under the given correspondence of vertices do not have equal measures. Angle A is not 90 degrees, but angle D is. Okay. Number 2, or E. Since triangle ABC is similar to BDC, not DBC, and triangle ABC is similar to triangle ADB, can we conclude that BDC is similar to ADB? Explain. So what they're saying is ABC, ABC. So if BDC is similar to ABC and ADB is similar to ABC, since they're similar to the same thing, they have to be similar to each other. That's the transitive property. So since similarity is transitive, triangle ABC is also similar to BDC, and triangle ABC is similar to ADB, implies that ABC is similar to BDC is similar to ADB. They're all similar triangles. Okay, transitive property. Identify the altitude in EFG. Okay, so let me move this over like so. So the altitude in EFG. So here's triangle EFG. The altitude is a perpendicular line drawn from the vertex down to the side opposite, and it is at a right angle or perpendicular. So GH is the altitude from vertex G to the line containing the side EF. Okay, simple enough. G, as before, the altitude divides a triangle into 2 subtriangles, resulting in a total of 3 triangles, including the given triangle. Identify them by name so that corresponding angles match up. Okay, so we need to be careful here. So again, I'm going to color code these. That I would highly recommend you do that. So if you have the big triangle out here, there's the big triangle. I will name that, and I'll use red, EFG. So I have triangle EFG. So what's the right angle in this? It is G. G is the right angle, so every other triangle that we name has to have their the right angle name come last. Okay, so then I'm going to switch to green. And I'm going to go with the next largest triangle, which is here. Okay, it's that one. And that is triangle EHG, GHE, whatever. It doesn't matter how you name the first one, but it definitely matters how you name the rest. So the next one, I'm going to use green, is triangle. So if we said EFG, we name the hypotenuse first, EF, and FG is the shortest side. So FG is the shortest, so I want the shortest side on this triangle to come up, and the right angle said last, and H is my right angle. So I'm going to put that last. Okay, G is a right angle. H is a right angle. So it goes last. FG, if you look at this, FG is the shortest side. So what's the shortest side in the green one? GH or HG? Well, I want the H to come last, so I'll call it GH. Okay, and then by elimination, E is the only side angle left. So I will name that triangle EGH. Right angle said last. Agreed? And then finally, the blue triangle, let me label it as blue. The blue triangle is the little one here. That's the blue triangle. So let me switch to blue, and I'll call that triangle. Well, the right angle is H, so that's got to come last. The shortest side is FH, so F goes there. And then the other angle we haven't named yet is G. And that is the easiest way to correspond parts. Okay, so let's see how we did. EFG, GFH, EGH. Okay, so they just put the blue one first and then the green one. So, okay, they match. So I can put this second and this. Oh, let's just leave it at that. Okay. And then finally, does the altitude divide EFG into two similar subtriangles as the altitude did with triangle ABC? And the answer is yes, because if I compare the green to the red, they share E and they both have 90-degree angles, so that's angle-angle similarity. If I compare the little one to the green one, blue to green, they share F and they both have 90-degree angles, so that's angle-angle. And if I compare the big one to either of them, the big one shares E with the green one, and it shares F with the blue one, and they all have 90-degree angles. So all of these triangles are similar. Excuse me. The fact that altitude drawn from the right angle of a right triangle divides a triangle into similar subtriangles, which are also similar to other triangles, allows us to determine unknown lengths of right triangles. All right, page 4, example 2. Consider the right triangle ABC below. Here's triangle ABC, the right angle is the B. Draw the altitude BD from vertex B. So if you were to draw an altitude and do it on paper, here's how you would do it. You would get a protractor. You would put the protractor's crosshairs and zero line right on AC, and then you would line up B like so and put a mark up here somewhere at 90 degrees, and then get a ruler and draw a segment from B down to AC, and there is your right angle. Okay, so there is the D altitude from B down to AC. Label AD as X, DC as Y, and BD as Z. So I should have this X. It was supposed to be AD. AD is just this tiny piece here. So here is AD right there. That's X. DC is Y. And BD is Z or Z. Okay, find the values of X, Y, and Z. Okay. So we have two right triangles that are set up proportionately. Actually, we have three, the original and the two smaller ones. So we have triangle ABC, triangle ABD, and triangle BCD. Okay, so I'm going to set up a proportion, and I'm going to use the big triangle ABC because I know all the sides, 5, 12, 13. The shortest side is AB, or the short leg is 5. So I would say AB, side AB is 2, And then if I'm going to find x, the short side of that, the short leg is x. So AB is to x as, and I know the hypotenuse of ABD because this is the right angle, so 5 is the hypotenuse. So I want the hypotenuse from the big triangle, which is AC, and that is 13. So it's going to be AC is to, so AB is to x as AC is to 5. Okay. Actually, let me put that as letters first, and then I'll substitute in my givens. So AB hypotenuse is to AC hypotenuse, and I'm sorry, try that again. AD, we're comparing side, side. So this is AD. So AB is to AD as AC is to AB. Hopefully that didn't confuse you there. Hypotenuse on top, short leg on the bottom for both triangles. Then I substitute in my givens. AB is 5, AD is x, AC is 13, AB is 5. Okay, so we have a shared side. The 5s will, well, they won't cancel. We cross multiply. We get 13x equals 5 times 5 and divide both sides by 13. So therefore, x equals 25 divided by 13. 25 divided by 13, it won't work. It doesn't even reduce, but 13 will go into 25 one time with a remainder of 12. So x is 1 and 12/13. Then I move on to find y. Y is DC. Y is the long leg of triangle BDC. So now we're looking at this triangle, this one right here, BDC. So we're comparing triangle BDC to the original triangle. And so since B is my altitude, I have to say my altitude of the triangle, A. And I said BDC. D is the right angle, so I have to say ABC. Those are the two triangles I'm comparing now. So if I'm going to take the longer leg, which is DC or CD, whatever way you want to call it, I'm going to compare that to the long leg of the original triangle, which is BC. And that is going to be set equal to the hypotenuse of triangle BDC, which is BC, to the hypotenuse of ABC, which is AC. So when I plug in my values for this, DC is 13, BC is 12. That equals BC, which is 12, and AC, which is 13. And I marked this one wrong. DC is not 13. DC is 13 minus X. I could do it that way, or I could just say Y. Okay, so we could have done it this way, but did you hear what I just said? We've already found X. So we could just take 13 minus that, which would be 12, 11, and 1/13. So let's just see if that's what we get when we do this cross multiplying. So when I cross multiply this, 13 times Y is 13Y. And 12 times 12 is 144. And I divide both sides by 13, and Y equals, and if I go 144 divided by 13, then I get 11.07, which is 11. And what's the remainder? So if I say 13 times 11 now, I get, 13 times 11 I get 143, and that's 144, so that's one remainder. So here's y. And it is the same as 13 minus x. So here's x. Okay, now we need to find z, which is right here, the altitude. So to find z, I'm comparing the little triangle to the original triangle. So I'm comparing triangle ADB. So if I'm trying to find z, that is the long leg. So it's the long leg is to the long leg of the big triangle, which is this side here, 12. This is the hypotenuse, this is the short leg, this is the long leg, and that is BC. So long leg of little triangle equals over the long leg of big triangle equals what we know about both, which is the hypotenuse of the little triangle, which is AB, to the hypotenuse of the big triangle, which is AC. Let me see if I did that right. Long leg BD is to long leg BC. Okay. Hypotenuse of the big triangle AC, hypotenuse of the little triangle AB. Okay. That's not what I'm trying to do. So where am I going wrong? I'm trying to find Z, which is BD. So BD is to BC, that's true. As AB, no, this is right, is to AC. So now I plug in my givens, and BD is my Z. BC is 12. AB is 5. And AC is 13. So when I cross multiply, I get 13 times Z equals 12 times 5. Divide both sides by 13, and Z equals 60 divided by 13. So it's 4. And then when I want to know the remainder, I just take that 4 times 13 and see how much less it is than the original 60. And I need 8 more to add to that. So that's my remainder. So it's 4 and 8/13. So that is Z. Okay, so X is 1 and 12/13, Y is 11 and 1/13, and Z was 4 and 8/13. Okay, so now we will look at a different strategy for determining the lengths of X, Y, and Z. The strategy requires that we complete a table of ratios that compares different parts of each triangle. Okay, so now we have this table. So we're going to set up proportions. So rather than having to scroll back and forth, let me erase this and I'll bring the diagram down here. Okay, so here we have the diagram again. All we have is that altitude that was drawn, BD, and the 3 sides of the original triangle. So in triangle ABC, the big triangle, it says to compare the short leg to the hypotenuse. So the short leg of the big triangle, now we're looking at ABC, short leg is 5. And the hypotenuse, here's the 90, look across, 13. Okay, so the ratio of the short leg to the hypotenuse is 5:13. The long leg is 12 to the hypotenuse, which is 13. And the short leg, 5 to the long leg, is 12. Okay, so then when we do ADB, ADB is this teeny meeny little one here, then the short leg is AD, and we called that, let me go back and see, draw altitude BD, I didn't label this, label AD as X, let me use green, AD is X, DC is Y, So this piece is y, and the altitude is z. Okay, so now that we've done that, looking at this tiny little triangle, its short leg is x. The hypotenuse was 5. Its long leg is z. The hypotenuse is still 5. Short leg to long leg is x to z. Okay, and then finally, the medium triangle here, CDB. Short leg is z. And the hypotenuse is 12 because this is the right angle. So this is 12. Long leg is y. Hypotenuse is still 12. And then short leg z to long leg y. And there is our table with ratio set up. All right, page 5, it says, our work in example 1 showed us that triangle ABC is similar to triangle ADB, is similar to triangle CDB. Since the triangles are similar, the ratios of their corresponding sides are equal. For example, we can find the length of x by equating the values of short leg to hypotenuse ratios of triangle ABC and triangle ADB. And that's what I've actually done already. Why can we use these ratios to determine the length of x? And the reason is because we can use these ratios because the triangles are similar. Similar triangles have ratios of corresponding sides that are equal. We also know that we can use ratios between figures or within figures. The ratios used were within figure ratios. Okay. Before I get on to that, let's find x, or did we already? Okay, so yes, of course, they just showed the work right here. And now it says, which ratios can we use to determine the length of y? And the ratio we can use to determine the length of y, we can equate the values of the longer leg to the hypotenuse ratios for these two triangles. So we're looking for y, and we're looking at CDB and triangle ABC. So CDB is this medium one, and ABC, the big one. Okay. Oops. Did I do that right? CDB, ABC. Yes. Okay, so I'm going to use this table to answer these questions. So let me copy it over so I don't have to keep going back and forth. Okay, so it says, which ratios can we use to determine the length of y? So I brought in the table. We already answered this. So I'm going to use CDB and ABC. And we're going to use long leg to hypotenuse. So that's this column right here. So all I have to do is take 12 over 13. 12 is to 13 as y is to 12. Cross multiply, and I would get 13y equals 144. Divide by 13, and I get y, shouldn't be equals. I get y equals, and then that was, I erased it, I think, yep. What was y? 11 with a remainder of 1. Well, 13 times 11 is 143 plus 1 is 144, yes. So there is my y. And it's so much easier if you just make this table. Okay, and then we're going to continue. Let me get rid of these. And if I come down to this part, it says use ratios to determine the length of z. So to determine the value of z, we can equate values of the longer leg to the hypotenuse ratios for ADB So for triangle ADB is here and the original triangle ABC. And we're going to do longer leg to hypotenuse, which is this column again. Okay. Notice where Z is. We have a Z, we have a number. So you have to use the right triangle and the correct triangle, and you have to use the proportion where you don't have two unknowns. So this is not helpful to either. This is not helpful, but we have a number and a variable in these proportions here. So we're always going to either use the long leg hypotenuse in this case or the short leg hypotenuse over here. Short leg to long leg in this triangle was not what we could use because we have two unknowns, if that makes sense. So now we're going to do these two triangles, this column here. So I'm going to say 12 is to 13 as Z is to 5, okay? And when I do that, I get 13Z equals 60. Divide both sides by 13. 13's cancel, and I get, I don't want an equal sign, I want an arrow. And that will yield Z equals, and 60 divided by 13 is, what was it? Should still be here. 60 divided by 13 was 4.1 or 4.6 or 4. And 8/13, remainder of 8, 4 and 8/13. So there is the length of Z. So using the table really makes it a lot simpler. Okay, so finishing up this page, it says, since corresponding ratios within similar triangles are equal, we can solve for any unknown side length by equating the values of the corresponding ratios. In the coming lessons, we will learn about more useful ratios for determining unknown side lengths of right triangles. Page 6 brings us to the end of lesson 21. Go to your problem set.